Right. Good afternoon, everybody. As Mark said, I'm going to talk to you about how we can visualize Nsight system traces with Paraver. Why we want to do that? We want a scalable visualization and being able to leverage some of the well-known features of Paraver as a well-established HPC performance analysis tool, but using that with accelerated workloads, accelerated applications, right now accelerated with Nvidia GPUs. So we get the Nsight system traces and we view them with Paraver. Basically, I will justify a little bit why this makes sense in the context of our analysis methodology and strategy, ours in our research group, but also in POP in general, how we do performance assessments in POP, and why we think this is also useful work advancing to more insightful and more comprehensive assessments for users, and also giving more tools to the analysts. Then I'll show you briefly how you can make the translator work, which is very easy. And then I'll show you some examples of how we analyze these traces with Paraver, starting with simple relevant metrics that we think that are interesting to see when we do some analysis, then showing how we can extract an efficiency model from our traces. And then I'll show you a more complex examples of when we have an inefficiency, how we can follow the lead of that inefficiency towards a more detailed analysis and the conclusion for that. As a starting point, so this is about tools. Of course, this is about using one tool, the other, translating things from one tool to the other. So why we do that? You know that for in the POP ecosystem, performance tools from POP, we have BSC tools. There are Xtray and Paraver, and then we have the Nvidia tools. All these talk, let's say, or the work that we have done since now, it's all centered in the Nvidia ecosystem because it's the GPUs that I have had access, let's say, and that we have access at BSC. But so the translator will be, and the examples will be translating traces from Nsight systems to Paraver. But this has not to be limited only for Nvidia. So we think that the idea behind what we do with the analysis is generalizable, and this can be generalizable to any accelerated workload. We're only missing the implementation part, let's say the translation part from other maybe ROCm profiler tools to Paraver again. But we think that this is generalizable. So we have these Nsight systems that gets comprehensive information from the system level, all the different programming models, behavior, hardware metrics from the GPUs, but we don't think it has a scalable visualization. We don't think it has a scalable visualization for large parallel executions. On the other hand, we have Paraver, which we know very well, and we can configure its views. We can configure new metrics with its DSL, and it's very suitable for large executions, for large number of resources. So what we did is, okay, let's try to translate these traces from Nsight systems to Paraver. We leave Nsight compute aside here because it is useful, but for analyzing very detailed and specific behavior of a specific kernel. And we think that this is something that you should and you can still do with Nsight compute. What we want to do is try to gain as much information as possible with Nsight systems without go to Nsight compute. So while having the whole system view information, still trying to go much as inside the kernels as possible. But of course, there will always be things that will be left for compute. So there's two main things that we think are important when we do our performance assessments. The thing is the concept of dynamic range. So when we think about large scale, it's not only the number of resources, so very big number of resources or long time execution, but also large number of scales. So being able to go from one scale, microscopic scale, to macroscopic scale. This is something that Paraver is allowed to do very well because we can navigate traces, we can gather knowledge in the more broad perspective, see metrics, see the general behavior of our application, and then when we see some effects that maybe are pinpoint to an inefficiency or show something that we quite don't understand, then we go just zoom in as much as we want to the microscopic behavior and try to understand that in detail. So we can work with very large scale runs, but still go up and down in scales through, so navigate through scales easily. Another thing we want to do also is to compare traces and to quantify the differences. And we want to compare traces across like different executions, so different traces. So maybe to understand how this small change, how this small improvement affects my execution. But we also maybe want to compare within the same trace. So maybe how the microstructure of my application is changing, is evolving through time. So in one step and then in n steps after, or maybe across processes, how one GPU behaves and then how another different GPU behaves at the same time. So this is something that we want to do. When we talk about scales and large scale, again, it's the number of scales, so the range of scales that we can navigate, but also the dimension. So we want to be able to navigate through time, but also navigate through resources and data. Through time, as I said, going from macroscopic behavior to microscopic structure of the application, work with very long traces, but being able to chop to, let's say, only the interesting part. With resources, the same. Maybe you have an execution of hundreds of GPUs that show something interesting, but then to understand that, we need to zoom in into the very specific one GPU that's causing that effect. But still, we want to, within the same tool, within the same trace, we want to be able to see both scales. And finally, data. We want to have all data, all performance information across time. We want to be able to combine this data, aggregate it, filter, and operate it using the well-known arithmetic operations and semantic functions that we have in Paraver. So given that, what we propose is that we get these Nsight system traces and translate them to Paraver. As we know, Nsight systems also provides multiple reports actually for distributed runs. So when we run an application that works distributed, Nsight systems will create different instances and then generate different reports for each of the processes or each of the nodes, depends. The thing is that we end up with different reports. With our translator, what we do also is merge these traces into a single Paraver trace. We aggregate all the resource information, all the resource models, so all physical and logical resources that have been involved into the execution, and then we merge that into a single trace that allows us even to understand interactions between the processes and between the tasks and the threads that then we can plot with Paraver. So basically, what we do is translating all the list of event types that you see here. This is an expandable list, so this is something that we are improving it as as long as the Nsight systems tool is also updated. Of course, we prioritize. We think, okay, which information is more relevant and more useful for the current analysis that we have. So we prioritize that, but this is something really expandable. So the software is developed in a way that what we translate and then how we build the internals to construct the Paraver trace is modularized, so it's easy to expand. The other thing that we do is merge these traces, as I said. So we get from a multi-node execution with multiple traces into a single trace. And of course, all this thing works well with the magic of Paraver when we have predefined configuration files. So what we do is we also provide a lot of predefined config files that already visualize the interesting metrics and the interesting events found in the trace into Paraver. These are provided also in the repository and with the package, so you can already use them when you translate your trace. So how do you get the package? Very easily, you just need, it's a Python package, so you can install it with pip. I suggest that you create a virtual environment to install it and its dependencies, but you don't need to. The thing is that you can install it also in your global environment. You can also use it in supercomputers. It is installed in Mare Nostrum, and you can easily install it in another supercomputer if you have internet access or you ask support team. And you only need Python and basic data treatment packages and SQLite, and that's all. This is something that you can install in your laptop or in a supercomputer. It works well in both. The thing is that maybe if the size of the trace that you're trying to translate is very big, or you have lots of reports to merge, this is it will work best in a supercomputer. How does it work? As I said very briefly, basically we have these type definitions. We have to extract the information first from the Nsight trace. So we will need Nsight systems when we translate the trace. Then we have these type definitions that can be expanded. And then we do the transformation and we leverage Paraver trace format. So we have to generate this resource model that has an overview of every resource involved. And then we create the event types, we define the event types, and we write the trace into a file. And how do we use it? So very easily, we just load the environment that we had, and you will see, as I said, we need Nsight systems as long as it is in your path, so that the system can find it, an installation of Nsight systems, you're good. The version of Nsight systems is relevant, so try to have the latest one. And then, as you see, we only need to provide the list of things that we want to translate with the T flag. So here we ask for the MPI things, NVTX regions, and the CUDA API calls. Then we put the M flag if we want to translate multiple traces, the list of all the nsys reps, and then the name of the output trace. And as you see, we just start to get a lot of messages, some warnings, also maybe. Here it's loading all the data from the SQLite, then some more warnings, and now the data treatment starts. As you can see, we got all the resource from the different reports combined. We know that we have 32 processes, each one with a GPU, with multiple streams, each GPU. It detected all the different resources, and now it's building the trace and writing it to disk. So once we have the trace, what we have is basic visualization as Paraver, as we are used to see. In a Paraver timeline, we have the time in the x-axis and the different resources in the y-axis. Okay, these different resources can be threads and processes, for CPU, and we can also have CUDA streams for GPU, and we can have them combined also. So in the same timeline, have the threads, the CPU threads, and its associated GPU streams in the same visualization. So for example, we can see things like CUDA API calls, so the different API calls that we have for CUDA. We can also see CUDA kernels, so all the kernel execution in the different streams in the multiple GPUs. MPI calls, of course. We can see a combined view of the CUDA API calls with its kernels. This is a visualization in the top right for 128 GPUs. So we can see all the behavior this is one step of machine learning training. So we see the forward and the backward. And we see the different rows are threads or GPU streams, so how they interact. And we can zoom only into one process, and we see that we have different one thread that's scheduling all the work for the GPUs, and then the different streams that execute each of the kernels. The communication lines that we see here, these orange lines that we can see, those are lines that tell us the dependency, so the relation between one kernel launch and its associated kernel. So we can easily see dependencies in time. So now we can jump to more different metrics, let's say different things that we can see that maybe are more difficult to see or to inspect and navigate with Nsight systems, and some metrics that we think are relevant that can be a first and an added help for the analyst to detect inefficiencies when analyzing accelerated traces. First thing, we have kernels in flight. Kernels just get scheduled by the CPU, by the CUDA runtime, and then they get in a queue, and the GPU runs that in a stream. The kernels that are sent in the same stream are executed serially. So the kernels in flight is the number of kernels that we have waiting in a queue to be executed. This is a measure to know how fast the GPU is going to execute, is executing the work, or how fast the CPU is issuing work. And we can paint this with a gradient. So if you look at the trace in the left, we see a gradient here where blue is high values and green is low values. So when we see a blue color, we know that there are more kernels in flight. So the intensity of work that the CPU is issuing to the GPU is higher. When we have greener areas, we see the opposite. We see that the CPU is having issues to provide work to the GPU. The GPU is faster to execute the work. We can then transform this to a histogram. So we want to analyze how this metric, kernels in flight, how it is distributed as in terms of occurrences. So we are spending more time with lower values or more time with higher values. And we can see that there's a specific region here marked with a red square that it says, okay, we have this specific point where all GPUs spend the same time on a higher value than the rest. So some specific region that we have a larger amount of kernels in flight. And if we zoom on this, we can go to see that again in the timeline. So as you can see, we can jump from a timeline, so specific visualization of a metric, how this metric appears in time. We then jump to a more aggregated way, so statistical analysis, how this value is distributed. And then from the statistical analysis, we can then jump back to the timeline. So okay, this behavior that statistically maybe shows some interesting for us, we can then go find it in the timeline to put that in the context of the execution. So we can know when this happens and how it is related to other things that can be happening at the same time or before or after. And one thing that we see here is that there's one specific GPU, one specific process, the number 1, 2, 3, that is having maybe the CPU is having some issues dispatching the work because the number of kernels in flight is always lower than the rest of the GPUs. And we can see that also in the timeline, that one doesn't show the same occurrences as the others. Now, another interesting metric is GPU usage gaps. This one basically shows when our GPU is idle, which is something that this one is directly related to an inefficiency because it's time that we're not using our resource and we want to use our resource as much as possible. So as again, we can start with a visualization of a timeline when in the time I do have my GPUs idle, and then we can convert that to a histogram to study that statistically. So more or less how it is distributed. Do we have a lot of small regions of not using the GPU, so very, very small gaps? Do we have a very large region of not usage of the GPU? How is that distributed? And we can then select the region that we're interested in. Here it's marked with a red square again. And then we jump back to the timeline. So we can see this small region here that it's showing us that probably at the end of the step. So this is a step in this timeline. So at the end of this time step, we probably have a long idle time for the GPU. So something that maybe we could address. We also see here that there's a specific GPU that is being idle more time than the rest. Well, two actually. The first one, the first process, and then also another one in the middle. It's taking more time than the rest that more or less show a vertical line, except that one in the middle. So this is something that maybe we could go understand why it's happening and if it is causing other problems. Another very important relevant metric, and this is something that especially AI machine learning workloads, we have to be like aware of that, and it's something that we can study. At first is the communication and compute overlap. So if we do want to overlap our communication time with other compute that doesn't depend on it, we can measure how much is our overlap going, and we can do this with this metric. In the timeline, we see the distribution of the different like overlap modes. We can have no communication at all. That's the value 0. That's the gray part. Then in the blue part, we have only one kernel going on, so meaning the communication kernel. This is the area that our communication is going along. So area that time that our communication is blocking everything else, and we're not using the GPU for anything else. And then we have anything that's below 1 means that we have at least another kernel happening at the same time as the communication. We can then, after we have inspected this in the timeline, we can jump into a profile to see the real impact of that. And in this case, we see that if we look at that with respect to total trace time, we see that in average, we're losing 11% of the time because of communication that it's not overlapped with anything else. But on the other hand, we have all the rest, 90%, that's communication that's being, 66%, sorry, 66% of the time we are communicating, but this communication is being overlapped. So this is good. We can also compare that with respect to the time that we are communicating. So how much time of my communication time is being overlapped or not. And in this case, we see that it's 14%. So maybe room for improve, but not bad if our intention is to try to overlap as much as possible. Be aware that here, when we talk about communication, when we translate the traces and we define like these metrics, for communication here, we mean all data transfer. So memory copies from device to host, host to device, or from peer-to-peer device, and also nickel kernels. So all kernels that are part of the Nvidia collective communication library that are basically kernels that prepare data and transmit data from one GPU to another. These kernels are also considered communication time. And another thing that we have, another interesting metric that we have is the tensor core usage in gem kernels. So we can start with a timeline of only the kernels, showing only the gem matrix multiplication kernels and also flash attention kernels. In this case, the examples that I'm showing you now are still machine learning training examples. Here we see matrix multiplication kernels and also flash attention kernels that we also know that are matrix multiplication mostly. And then we have the tensor core usage as a percentage of the peak, but as a sampling. So we see the whole trace, how our tensor core is usage by sampling, by every specific point of time, the percentage of cycles that we have been using the tensor core. We can then convert that maybe to an aggregated view across all GPUs to see in general our application. So this is application level, not process level. In general, in our application, how the usage of the GPU, the usage of the tensor core is going. And we can see in a function line, regular function line. But then maybe we can see we want to see the specific kernel. So this is a very aggregated view, and it's good for getting an overall perspective. So we can see that in average, our application doesn't go much beyond 50% of the usage, peak usage of the tensor core in average. But then we can get this information of tensor core usage and put it in the context of the specific gem kernels. So we average the sampling that we have for each of the kernels, each of the matrix multiplication kernels, and we end up with this timeline that you see here. So now we can go zoom in and see for a specific kernel what was its average tensor core usage. And of course, if we have this, if we have this in the timeline, we can also have this in a profile, so we can see the numbers aggregated. And in this case, there are three fast observations that we can do with this example trace. The first one, for example, is that we have high variability between GPUs in some of the kernels. Specifically with the flash attention kernels, we see a high variability in usage between one GPU and the other. We can also see that gem kernels, so specific gem kernels, also show different tensor core usage in average. So there are some gem kernels that are better at using the tensor core, and other gem kernels that don't use the tensor core as much. And finally, we can also see that their specific CPU, specific process 13, and its GPU, a specific GPU that shows a very different behavior in almost all of the kernels. So usually lower usage, but sometimes higher usage than the others. But consistently, we see this specific GPU that's showing different behavior in tensor core usage. So this is more or less the metrics that I wanted to show you. This is of course, we're not limited to these metrics. This is something that we can expand always with Paraver. We can compute something more useful for every specific analysis, and it depends, of course, of the what is the purpose of our analysis. Sorry, what is the kind of the application? Because in this case, I'm showing you a lot of metrics that are very relevant to machine learning, but this can be applied to all the HPC, like classical applications that more and more recently have been transitioning into GPUs. So this is, of course, something that you can discover more metrics, and the interesting thing of this approach is that you have all this data, you have this scalable way of visualizing data, and you can just invent or compute new metrics with Paraver very easily. Now, from specific metrics, we can jump to the efficiency model. Efficiency model is something that's part of the POP project. It's something that we work on, and it's the first step for us to obtain, let's say, a fair and comparable way of inspecting the efficiencies of an application. It's our first step to see, okay, how this application how efficient is this application, and I can compare this efficiency with other applications, with other executions with the same application, etc. So this is the first step, and of course, one of the advantages or something that we want to leverage when visualizing the traces with Paraver is also, of course, computing efficiency metrics. So we can put all these GPU analysis in part of the POP ecosystem and the POP way of doing performance assessment. This efficiency model is the same model that Marta presented just a month ago for the TALP metrics. This just a little bit different. We have less metrics here, but I'm only showing you the device efficiency. But because that was TALP, and in this case, depends on the programming models that you're using, it can be a little bit different, but the device metrics, the device efficiency model are the same. So Marta presented it last month, and what the thing interesting here is that we can compute this very easily with Paraver. We can leverage the infrastructure that we already have. So from a Paraver trace, from the Paraver format, we can get kind of a basic analysis tool, model factors tool that gets these metrics provided a CFG. And then, of course, we can have some computational scalability metrics as we have for the efficiency model of the OpenMP and MPI efficiency model that we already have. For POP, that we have computational scalability. This is something that is a work in progress, as Marta mentioned last month, and we're still trying to think, okay, how we could construct a computational model for GPUs, because as you know, it's a little bit different than a CPU. And we also can have these complementary metrics. That's where all of the metrics that I have shown you can fall. So having an efficiency model is also a way to put a little bit of order in all these metrics and have a more clear and standardized way to begin your analysis, gather some basic information that you think that maybe can be interesting, and then from that jump to the detailed analysis, jump to the very specific inefficiency that you want to study. As an example, I'm showing you here a trace of that's using 4 GPUs also, and with this, using the different configuration files for the model, for different efficiencies of the model, we can see how, in this case, the efficiency model would be. The almost perfect load balance. We don't see a problem with load balance. We see 90% of communication efficiency. That's mainly due to these serialized memory copies that you see here in the middle. Sorry, there's no legend, but I only want to show you the structure and like the brief idea of how this translates. You see the three serialized memory copies in the middle, so that's accounting for communication efficiency. And then we have orchestration efficiency of 50%, so clearly showing us that all these GPU gaps, all these usage gaps that we have in the GPU streams, this is something that we should address. So now I'll go to applied examples and finish here. Let's start with the useful time and load balance. So now that maybe we got the load balance efficiency, this is a different example trace, right? Here we also got the load balance efficiency metric from the model, from the efficiency model, that's a 92%, and we go to see the trace. We open the GPU useful time, so we see in a gradient our useful bursts. So when our GPU is doing useful work, we see for longer bursts a blue color, for shorter bursts a green color. And we can see that there's GPU 13 that's steadily across the training step has higher kernel durations. So their kernels always take more time. And we can see that then this has an effect because it's the last one to end. So all GPUs end before this one. So in this case, we could see we can relate this with the GPU with the tensor core usage that I showed before. That was if you remember, was the same GPU, the GPU 13 that had lower tensor core usage. So this can impact the execution time of the kernels, making these kernels take longer. And then we see the macroscopic effect, which is a 92% load balance efficiency, which is not bad, but you have to consider that this is only 16 GPUs run. So if we scale up, this will probably go worse. We also see that this impacts communication phase at the end of the step. So all of the GPUs are waiting. And we also see that high execution time for the same GPU that we observed earlier. This is something actually that we are still studying. We're still researching because we want to discover exactly why we see this different behavior, and we are studying this with here inside at BSc. Another thing that we can study are, again, how matrix multiplication kernels behave at this microscopic scale. So starting with an aggregated view of the matrix multiplication kernels, we have these different kernels. These are cuBLAS kernels. The only difference is, the tile size and the operations, but they are all general matrix multiplication kernels. What we are seeing here is the histogram of the kernel duration. So how this type of kernels, the duration of these kernels statistically across the execution. And we see these two, the green and blue, that have a bimodal wave. So these have two modes. If we focus on the green and the blue, we see that in two different times of the execution, we can find the same progression. So first the blue one and then the green one. But in one case, the blue is short and the green is long. And on the other case, the blue is long and the green is short. On the other hand, we have in another stream running an equal or reduced kernel. And this is relevant because what we saw here is that the nickel kernels that run overlapped with the gem kernels are causing our gem matrix multiplication kernels to take longer. And we observe this then inspecting the number of the GPU hardware metrics. If you see in the green longer case, first we have square number 1 that shows the blue gem kernel. This runs perfectly. The tensor activity, you see that is blue, so high tensor activity, everything is perfect. Then starts the green one, and at point number 2, we see that we see NVLink activity. if you look at the row with NVLink activity, we see some NVLink activity. This means that the nickel kernel is communicating. At this point, the tensor activity for that gem kernel goes down a lot, and it doesn't recover. So we don't see blue in the tensor activity, so higher values for the tensor core activity, until 0.3, where the nickel, the NVLink activity, so the data transmission activity, finishes. This is suggesting us that having some NVLink activity, so data transmission due to nickel kernels, is interfering with gem kernels that want to use the compute resources of the GPU. So this is something that we kind of observed in a microscopic way, but then when we zoomed in and we studied these particular examples compared with the GPU metrics, we saw that this actually had some relationship and that had an impact. And in this case, you can see that the same kernels, the same execution progression showed different behaviors depending on if we had some communication overlapped or not. In the blue longer case, it's the same, but the opposite. We start the blue kernel at point number 2. We have this NVLink activity, intense NVLink activity here. You can see the blue color in the NVLink row. So here the tensor core activity goes down, and when the NVLink activity finishes, the tensor activity goes a little bit higher. But still, the whole gem kernel, blue gem kernel here, takes a lot of time. So it's impacted at first time by the NVLink activity, and then takes a lot of time. Instead, the green kernel here just shows very high tensor core usage, and it has no interference with any nickel kernel going on. So basically, we see that we are actually able to see very microscopic behavior inside kernels without going to compute, inside compute. Only if we have these GPU metrics and we can get a sample rate that's high enough, maybe with this sample rate, you can see that we see internal behavior happening inside the kernel. We can see how this changes across time. So we don't need to go to inside compute for most cases. And you saw that this gave us interesting insight of the impact of overlapping communication and compute in a machine learning training workload. And again, this is something that we're also currently researching and here at BSc, and we plan to go deeper and to discover exactly what's going on and how this impacts executions and applications, ML applications, and in general any application that uses a nickel and wants to overlap. So that's all from my side. Here you have some useful links, the repository of the tool, some documentation where you will find basic usage of the tool, the feature list, so the status of each feature, so you can know maybe it's something that we have been trying to implement and it's still not done, but we're thinking of it, so you will see it there, and some troubleshooting if you have any problems. And then, of course, all the CFGs, so for the metrics that I have presented, every CFG is included in the repo. So if you download the repo or go to the CFG folder in the repository, you will find all these CFGs ready for you to load with your translated process. And of course, if you have any use case, application, or something, don't miss the opportunity and apply for a POP assessment, and we'll try to provide useful insight on the performance of your application. Thank you for your attention, and I will now answer some questions. I guess we have time, so thank you.
Yeah, thank you, Mark, for this interesting presentation. Yeah, we have quite some time for questions. There are already a few questions in the chat, and maybe there are some more in the audience. I'll go through the questions in the chat right now, and you can either enter them, enter your additional questions there, or raise your hand and then unmute yourself. So the first question is, can you see overlap between GPU kernels and MPI communication? Which relates kind of into the second question, does it consider time in MPI for non-nickel runs? So, or did you only consider pure nickel communication?
Okay, so I think that this question, from the perspective of the traces itself, and you can compute that. We have the MPI information, so we can see when in a same process we have GPU activity and some MPI activity going on the CPU. We can overlap this with Paraver and obtain a metric that's interesting from here. Something notable also is that depending on the implementation of MPI that you're using, probably the MPI call will have an associated memory copy in the GPU side. So internally, MPI, when you're using CUDA-aware MPI, and you issue an MPI communication between two addresses that are in the GPU address space, you will probably end up seeing a memory copy that's peer-to-peer. So from one GPU directly to the other. This, of course, depends on the MPI implementation and in the links, hardware links that you have in your machine. But it is something that can happen. So in this case, what you will be seeing in the end is the memory copy in the GPU side. So you can see the impact of the MPI in terms of communication in the memory as a memory copy. Maybe you don't have that. Maybe you have pure only MPI, so you transmit the data first, you do the communication on the CPU, and then you transmit it back. If this is the case, you can create a visualization with Paraver to show you when you're waiting for MPI. But in this case, I think that the question is more related to the model. So how the model interprets MPI communication on the GPU side. And this is something that I think I cannot answer right now because it's more related to the efficiency model and not the way of visualizing things. But it's interesting, and it's something that when we define the efficiency model, I wish Marta was here to talk about this, but when we define the efficiency model, this is something that we also had to think about. Yeah.
Yeah. Okay. There's another question related to MPI. So in the case of MPI jobs, how does it account for data movements over RDMA, which are not visible from nsys systems yet, as far as I know?
Again, if the MPI is using is relying on the memory copies of CUDA, so if internally is calling memory CUDA memory copy, you will see the memory copy. So you will see the MPI call, and then inside it the CUDA API call, and then in the GPU space the copy itself. In the case of RDMA copies, direct copies that don't have an effect in the runtime perspective, let's say in the programming model perspective, in this case, I guess that we wouldn't see this, but of course it depends on Nsight systems. So what we do is basically translate what we have in Nsight systems into a trace. We of course transform a little bit the data and make it more Paraver friendly, so that every kind of data that we have is something that's a function of time. But if there is something that it's not in Nsight systems, of course, we cannot get it in Paraver. So we rely a lot on what Nsight systems is capable of acquiring. And as far as we've worked for now, we think that Nsight systems is capable of acquiring a lot of data, more data at least that we find with Extrae. But maybe there's some other tools that can gain acquire information that we cannot acquire with Nsight systems. I don't know.
Okay, thank you. Then we have a question regarding the tensor core metric that you've shown. So does this show the time in which at least one tensor core is active, or some sort of metric describing how many tensor cores units are being used on a device?
This is something that we don't know exactly. And because on Nvidia side. They give us some kind of estimation between all the tensor cores, and they create this metric, and I guess it's the average of all the tensor cores. So the usage in the percentage of peak usage of each tensor core averaged, I guess. But this is something that um, it's even difficult for them, like for the hardware, to obtain this metric. Um, and what they say is that they do some kind of estimation, but it's totally on the Nvidia side. So they don't really provide the exact definition, or at least I have not found the exact definition of that metric related to the specific hardware. I guess my guess is that it's an average of all the tensor cores.
Yeah, so that relates into my question. So how difficult is it to do this conversion? So how stable is it over versions? Does it change all the time? Do you need to do some reverse engineering? Talk directly to the Nvidia folks about it? Do they expose this information? So yeah, basically the engineering aspect of
Um,
putting the converter together.
it it has not been easy at all. It's getting easier recently. So when I began doing this, there was very few documentation on that, and it was a lot of reverse engineering. Nsight Systems also is a tool that's evolving very rapidly, so they update it very regularly, and they are not simple updates. When they update, they change a lot of things. Usually, they add useful functionality, interesting functionality. So this is good, but it changes a lot. And what we rely on for acquiring the data is on the SQLite export. So the nsys rep, it's a proprietary format. We don't know. But from that, we export an SQLite with all the information, and from that, we acquire the data. The thing is that the SQLite schema reference, changes on every version. Not a lot, but changes. And usually they change it exposing more data that originally was there, but maybe it was not exposed. Or they change the way that they exposed that data. So it has been difficult. It was a lot of reverse engineering at the beginning. Lately, the documentation, specifically on the SQLite schema, has been more stable and more informative. So that made things easier. And for some specific things that I didn't know, I asked directly NVIDIA guys, and they have been very helpful. So they understand the need. They see that, and they are actually interested in people just getting integrating their tools into custom workflows and in business workflows. So they are very okay with that, and they help a lot. Yes, to understand how some things that are not obvious work.
Mhm. And do you see any any limits on scalability or trace durations that would be caused by the the translation and merging of the traces? I mean, this is a costly process, right? So what's your current take on scalability?
Yeah.
What do you say is reasonable to
For
try?
So the main issue right now is memory usage, because this doesn't scale. I think it does not scale linearly, and I think so. I think it's an engineering problem, really, because if we change the way of doing this in a more streaming, let's say, way, so we don't load all the data at the same time and we treat data in a streaming way, we could solve the memory scalability requirement. So, but right now it is a limitation. Yes. In terms of time, it scales linearly. So if you load more traces, you will have, so it scales with a number of events that you're translating. There's no I think there isn't any region which is quadratic or something like that. We just,
Mm.
if you have more events, you get more time, but it's something doable. Yes. Uh, Still, we're translating to Paraver format, which is ASCII format. So size of traces is something that can be
Yeah.
limiting, but this is not only for Paraver. I think that trace size is something that in general, or in all tools, more or less, it's something to take into account. More in Paraver, of course, I think more in Paraver, but I think it's a common issue.
Yeah. I know what you're talking about. Okay. Do we have any further questions? Um, are there any plans to support rockprof traces?
Sorry, to support what?
Rockprof traces, so for AMD
Yes,
GPUs.
yes, yes. We want to work towards, let's say, any to PRV or accelerated to PRV. So the current plans are to support rock prof traces, yes, and we think it won't be very difficult because, as I said, it's very modularized. So as long as we acquire the data and we define how to acquire this data, if we get more or less tables that resemble the tables that we have now, the rest is already done, the rest of the process. Of course, the difficult part will be the reverse engineering of how these traces contain the information. Another interesting thing that we want to support too also is PyTorch traces or Kineto traces in general. Basically because we have seen that PyTorch traces are very useful for machine learning guys because they contain information related to the PyTorch runtime and related to the model itself and the training itself. Something that's not specifically performance information, but it's information related on how the model is training, and this can be related to performance then. So is something that we want to have.
Yeah, makes sense. Any further questions? That doesn't seem to be the case. Then I would like to thank you for this interesting
Thank
presentation.
you for your attention.
And yeah, I wish everyone a nice weekend. Goodbye.
Bye. Goodbye.